All right, we're going to start with nitrogen nucleophiles. The last section, 19.5, we dealt with oxygen nucleophiles, and we'll look at several other types of nucleophiles that react with aldehydes and ketones today, because chapter 19 covers aldehyde and ketone chemistry. All right, section 19.6, it says here that under acidic conditions, an aldehyde or a ketone can react with a primary amine to form an imine. And so I think it's key that you remember that when you form this new functional group called an imine, that the reaction only occurs with a primary amine. And what we're going to see in a few slides is that when you react an aldehyde or a ketone with a secondary amine, you get a different kind of product. I also told you that an imine is oftentimes referred to as a Schiff base because of Hugo Schiff, who discovered them. And so we treat the aldehyde or a ketone with a catalytic amount of acid. Remember, that's what these square brackets refer to. It refers to an acid catalyst, our primary amine. And then when it says minus H2O, that means that we're removing water from or during the overall process. Now, it's important, again, that you understand that this reaction requires acidic conditions in order to work. Let's take a look at the mechanism and see if we can make some sense of it. It starts with a nucleophilic attack by the amine on a carbonyl group. Now, this is a little bit different than when we looked at acetal formation, where the first step was a proton transfer to protonate the carbonyl. And we're going to talk about that more in a second. So first we have our nucleophilic attack, then a proton transfer, and then another proton transfer in order to give us a carbonylamine. And you need to know the structure of a carbonylamine. And the way our textbook breaks it up is he says you can remember that we have 1, 2, 3 steps to our carbonylamine, and then we have 1, 2, 3 steps again in order to form our imine. I just want to point out that after this proton transfer here, and after the loss of our water, so here's our minus H2O right here, that the last proton transfer involves an intermediate where the nitrogen is protonated. And then we have a base come along and remove that proton, and we form our imine. Now, you might have been looking at that acid catalyst that's required for this reaction and thinking, okay, well, when I was making an acetal, I used a mineral acid like, let's say, HCl or sulfuric acid or PTSA, para-toluene sulfonic acid, and those are strong acids. And if we were to take an amine, like a primary amine, and treat it with a strong acid like HCl, the equilibrium is going to go completely to this side, right? We're going to have exclusively the ammonium ion. Now, that's all well and good, but an ammonium ion is not a strong enough acid to protonate an aldehyde or a ketone. So that means we'd be stuck, okay? And so what that tells us, or what I'm getting at, is that we're going to have to mitigate or watch or control the pH of imine formation very carefully. Let me show you what I mean. It says here that for imine formation to occur, the pH has to be just right, around 5, somewhere in the 4 or 5 neighborhood, or the reaction is going to be too slow. Of course, if you're at a lower pH, a more acidic pH, then all the amines are going to be protonated, and then you're only going to have ammonium ions. You won't have any amine left at all to attack the carbonyl. That's not really helpful. And then if you're at a higher pH, it's going to be not acidic enough in order to catalyze the reaction effectively. And so again, you have to monitor the pH of these reactions very carefully. But what you really need to know moving forward is that an acid catalyst plus a primary amine with an aldehyde or a ketone and the removal of water will give you an imine. Next, we're going to look at a new functional group called an enamine. Here's an enamine. Under acidic conditions, an aldehyde or a ketone reacts with a secondary amine to form an enamine. Right now, I'm probably just doing review here for all of you, but you should know that this is a primary amine when you have an NH2, and when you have two R groups on your nitrogen, like this would be a secondary amine. Okay, so I just want to clarify that if you're unsure about that. Again, we take our ketone or our aldehyde. Here they're showing cyclohexanone with a catalytic amount of acid and a secondary amine, shown here, removal of water, and we form this enamine. And you can probably tell where that name comes from. Okay, we have an amine here, and then we have an alkene here. So we call that an enamine. Again, the reaction requires acidic conditions to work, and the mechanism is identical to that of amine formation. It's the exact same mechanism that we looked at a couple of slides ago, except for the last step. Now I'm going to go back up here, and you probably remember that in the last step of amine formation, we had a proton on the nitrogen with a positive charge, and so the proton transfer resulted in the formation of the amine via this deprotonation. Now with an enamine, there's not going to be a hydrogen on that nitrogen. Let's take a look. The first three steps, we start with our nucleophilic attack and two proton transfer steps. Then in the second step, the second half of the mechanism, after the formation of the carbonylamine, do a proton transfer followed by the loss of our water. There's our minus H2O. And here's the key difference, which is this deprotonation here. Notice there's no hydrogen on this positively charged nitrogen. And so our base is going to have to remove a proton off of one of these carbons here in order to form the double bond. This slide just summarizes two reactions that we've looked at already. The reaction between a ketone or an aldehyde, again here they're just showing a ketone, with an acid catalyst and a primary amine, and then we form an amine, or an acid catalyst and a secondary amine, and we form an enamine. And notice that they've even gone through the trouble of highlighting the very last step of the mechanism and showing why you end up with different products. Now, this is just a mnemonic that my students taught me a number of years ago. They said, okay, well, if I have a primary amine, so the number 1, you write it like this, amine, like that. So it kind of looks like the number 1 kind of looks like the letter I, maybe. I don't know. And yeah, and the other one they showed me is even funnier. Is this one here? If you write the number 2 like this, and you write amine. I had to write this down this morning. So if you kind of put a hat sort of like that on the number 2, it kind of looks like the letter E for the enamine. I don't know if that'll help anybody, but help my students. I don't know when they showed me this a number of semesters ago. So the amine is the result of a primary amine in an acid catalyst in an aldehyde or a ketone, and the enamine is the result of a secondary amine, acid catalyst, and an aldehyde or a ketone. We're going to look at some more chemistry of amines and enamines in a little bit, but before we do that, I want to show you another functional group that you have to be aware of in a new reaction called the Wolff-Kishner reduction, which is a 2-step synthesis for converting a ketone into an alkene. Now you might remember that we've learned the Clemmensen reduction for doing this earlier on. And the Wolff-Kishner reaction involves the treatment of our ketone with this molecule right here. So I'll highlight it for you. This molecule here, NH2, NH2, this is called hydrazine. Hydrazine. So when we take our aldehyde or ketone, we treat it with hydrazine and a catalytic amount of acid, remove water. Okay, this is going to be the exact same mechanism as like the formation of the first step is the amine formation between the ketone and the hydrazine, which is like a primary amine, and then the second step is like an elimination. Anyhow, the book doesn't cover the mechanism in any detail, but from the hydrazine and a ketone, we end up forming what's called a hydrazone. And then brand new reaction that I wanted to show you right here, which is where we treat that hydrazone with potassium hydroxide in water, and we heat that up. And this is called a Wolff-Kishner reduction. So make sure I spell it correct. The Wolff-Kishner. All right. So the Wolff-Kishner reaction, and that is a way to reduce. Overall, it's a way to reduce a ketone down to an alkene. And you can also see that this reaction is essentially irreversible because you end up forming nitrogen gas as a product. Now that nitrogen gas is going to go off into the atmosphere, and that's going to drive the reaction forward. Here's the mechanism of, or the second part, the mechanism of the second step of Wolff-Kishner reduction. So the first step is the formation of the hydrazone, and then this is the step where you take the hydrazone and you reduce it to the alkane. Okay, so you can see that it's a proton transfer in the first step. Then we can draw a resonance contributor where we put the negative charge down here on the carbon, and then that can abstract a proton from water. We do another proton transfer with another equivalent of hydroxide, and that is where we end up liberating our nitrogen gas right here in this step. And then we just do another proton transfer, and there's our alkene. So the mechanism of Wolff-Kishner reduction. Just to, 1, 2, 3, 4 proton transfers and a loss of leaving group. Hopefully you've noticed the many similarities between the acid catalyzed mechanisms that we've discussed. Okay, so whether it was amine formation, enamine formation, or acetal formation, notice one thing, that under acidic conditions, the reaction species should either be neutral or have a +1 formal charge. If you're ever drawing a mechanism and you have a -1 charge under acidic conditions, that's a red flag immediately that there must be something, untoward happening there. Well, let's take a look at some practice problems. And we'll start with this one here, question 19.15a. Here we're taking a ketone. This is cycloheptanone, so we have a ketone. And remember that when we had a ketone or an aldehyde plus an amine, we could end up with an amine or an enamine. Now, in the first case, we're reacting with ammonia. Darn it, I didn't see ammonia before. All you talked about was primary amines and secondary amines. Does anybody have an inkling how ammonia would react? Do you think we would form an amine or an enamine using ammonia as your source of a nitrogen nucleophile? Anybody have an idea about that? Yeah, Sean says an amine, and you're absolutely right. What's the rationale for that, Sean? It would be that when you have your intermediate in the last step, you're going to have a proton on the nitrogen with a positive charge. In fact, you would have 2 protons. And if you're unsure about what I'm talking about, let me back all the way up here. We've got time. Let me just go all the way back here. Where was I? All the way back here. Okay, so in the last step, and what I'm talking about is this step right here. If you used ammonia, right, instead of an R group here, you'd have an H. So that means that in this intermediate, you'd have 2 hydrogens, right? So of course, you're going to end up forming an amine like that, okay? So to summarize, if we go back to this slide, where was my summary slide here? If you do this same reaction, okay, and if you use H plus and ammonia, you're still going to end up with an amine, right? But instead of an R group, you have a hydrogen directly attached like that. Okay, so I'll see if I can go from here to here, and over here like that. Okay, let's go back to that problem. Here it was. So, like Sean said, we're going to form an imine. And the imine that we're going to form will look like this. We'll have our 7-membered ring. Do my best to draw that. There we go. And we're going to have our double bond to nitrogen, and it's going to have a hydrogen attached directly to it. Now, and that's the final answer, so maybe I could move it over far away. There we go. All right. There we have it. Give you a second to take a look at the next one while I'm moving things around here. And the next one, we have ketone, and we have a primary amine. And if we're reacting with a primary amine, could anybody tell me, will we form an imine or an enamine? Not a trick question. Yeah, thanks, Kylie. Absolutely. And Sarah, you're both correct, right? If we take a ketone or an aldehyde plus a primary amine, we always end up with an imine. Now, if you're struggling with the imines, I can show you how you would draw that. You start by drawing the 5-membered ring. I'm just going to tilt it upwards here. I'm just changing the orientation. Draw the double bond, but instead of drawing an oxygen, you put a nitrogen on the end. Okay. Now here we have an R group, right? In the case of ammonia, we had 1, 2, 3 nitrogens. Here we have 2 hydrogens and our R group. And so our R group is going to be over here. And we'll draw it in. It's a cyclopentyl, like that. And this is our imine. So again, a ketone plus a primary amine gives us an imine, like that. Okay, there we go. So imine formation. A couple of reactions that are kind of, covered very quickly in our textbook. And I decided to not put them in my slides, but rather discuss them with you in a slide, is if you imagine this ketone, let's just, take things one step at a time here on this slide. Okay, if you imagine this ketone here, so this is 3-pentanone. If you were to take that ketone and say react it with this primary amine, okay, catalytic amount of acid, removal of water, what would you get? Well, I think you probably got it by now, that you would end up with something that looks like this, where you have the double bond, and you have your nitrogen, and you have an R group. If you use this interesting looking molecule here, so this molecule right here, I'll write it down over here. When you have a hydroxyl attached to an amine, this is called hydroxylamine. Okay, so hydroxylamine, and when you react your ketone with a catalytic amount of acid and hydroxylamine, instead of an R group there, you end up with this, okay? And this is called an oxime. Sometimes people pronounce it an oxime, okay, which is totally fine with me. I don't care how you pronounce it. But you end up forming this oxime or oxime, okay? And the book doesn't go into a huge amount of detail about oximes at this point, but I'll just tell you that oximes can be used to synthesize heterocycles like isoxazole. And I don't expect you to have isoxazole memorized, but it's always good to know why this is called isoxazole. And it's a heterocycle that could be used in maybe a potential drug. And so an oxime or an oxime would be an intermediate that you would use to synthesize that kind of heterocycle. And you have to be fully aware of what an oxime is. In fact, if you read the book, which I'm sure you all did, you would know that he placed some importance on this. Okay, so it wasn't just something that came up in a question and you don't have to know. The same thing applies to the second reaction here. So let me just draw a line to divide that. If you use hydrazine, and we looked at hydrazine already today, so if you have NH2, NH2, this is hydrazine, right? The same rationale applies. Okay, if this was an R group, you would end up with, something that looked like this, where you have a double bond, and then you'd have an R group. But we don't have an R group, we have an NH2. And so when you react a ketone or an aldehyde with hydrazine, catalytic amount of acid and removal of water, you end up with a hydrazone. Okay, and hydrozones have, you know, a few uses as well. And one of the things that I've used hydrozones for in my life is to make another kind of heterocycle that I made a lot of a long time ago in a program I worked in, which is this heterocycle, and this is called an oxadiazole. Okay, again, you don't have to have these heterocycles memorized. Okay, not at all. I'm not going to ask you any questions about those on a quiz, but you know, in case you have an inquiring mind, and it's like, why would we do this? Well, that's why you would do that kind of chemistry. Okay, but you do have to know everything that's inside, you know, this green box here. Okay, you have to know what hydroxylamine and hydrazine are, and you have to know what an oxime and a hydrazone are. Okay, let's move on and take a look at some questions that deal with enamines. It says here, predict the product of each of the following reactions. You can see that we're taking a secondary amine. This is a secondary amine, and we're reacting it with a ketone. And you notice that before they had the ketone over here and the amine over there. It doesn't matter. That's neither here nor there. We're treating it with a catalytic amount of acid. Well, here we're going to form an enamine. And if we draw the ketone out, let me show you how you would do this. So you draw the 5-membered ring, okay, and you're going to connect it to the nitrogen. Okay, now what else is connected to that nitrogen? It has 2 R groups. They just happen to be big old cyclohexyl groups. So we'll draw those 2 cyclohexyl groups in like that. Now we've got our amine, but we don't have our ene, right, from our enamine. And the double bond is going to be here, okay? And now if you drew it there or there, that's neither here nor there. Either way, it's the same thing, okay? But you're going to end up with an enamine. And if you're like, well, how do I remember that I'm not going to have a double bond on my nitrogen? Well, think about it. If you had a double bond on your nitrogen, like, then it would have a positive charge, and you need a neutral molecule. And so there's your enamine. Okay, so we'll write that in here. This is an enamine. And there's lots of interesting enamine chemistry that's not covered in this class. We're going to look at a little more of it later on. Now, here's an example of an intramolecular reaction. Most of the reactions that we look at in this class are intermolecular, between 2 molecules, but here's an intramolecular reaction. Why do I call it intramolecular? Because we have a ketone here, and we have a secondary amine right here. So they're both in-house. They're both on the exact same molecule. Now, this is where counting carbons, and in this case, nitrogens, is really important. So let's count carefully. And this numbering that I'm putting on here has nothing to do with nomenclature. This is more just to kind of do a little bookkeeping here to help me not make a mistake. So we have 1, 2, 3, 4, 5. And the reason I'm not putting 6, 7 out here is because they're not going to form the ring, right? Think about it. In my first step in the synthesis, okay, in the first step of this reaction, is that my amine is going to come in and it's going to attack the carbonyl like this. Okay, now I'm not going to draw out the whole mechanism. I don't have to do that. I just need to draw my product. And if I'm reacting a ketone plus a secondary amine, I'm going to form an enamine. Let's draw what that enamine would look like. So I'm going to start by drawing my aromatic ring because I know that is intact. That doesn't get changed at all in this reaction. There we go. Now let's count here carefully. I have 1, and then that's going to connect by this curved arrow, right? Curved arrows represent the formation of a bond or the breaking of a bond. Now this one starts on a lone pair and ends up on a nucleus, so that is bond forming. So that means between number 1, okay, that's going to form a bond to a nitrogen, right? This nitrogen that I labeled number 5. Give me so far. Okay, I know we haven't, like, yeah, we haven't finished product. Okay, good. Because I just want to make sure you're with me on the bookkeeping, on, you know, where is everything located. Okay, good. All right, now we have a 5-membered ring. Okay, all I'm doing is counting. I'm not doing anything more intelligent than that? 1, 2, 3, 4, 5. Okay, so I've got 1 and 5. That means I have to have 2. Oops, I want to use black pen. Where is it? 2, 3, 4. Boom. There we go. Now I've got the 5-membered ring. Now what else? We know that on carbon 3 we have the 2 methyl groups like that. Okay, and if it helps you, I could number them 1, 2, 3, 4 like that. Got the 2 methyl groups. You notice that on on the nitrogen also has an ethyl group on it. Now, just like in this example here, where the nitrogen has 3 R groups attached to it, this is going to form an enamine. Now, the only place that double bond is going to be right here. Oops, maybe that's going to be right here, like that. And there's my enamine. So again, what's the result? I'm taking ketone plus the secondary amine, and I'm making an enamine. Now, if you're confused about my placement of the double bond, let's think about it. If we erase it, it can't be here, okay? Because if it was here, then you'd have 5 bonds to a carbon. That's the old thanks for coming out. We'll never call you again, okay? If you were to put it here, then you'd have a positive charge on your nitrogen, and that's not correct either. So let's forget we ever did that and put our double bond of our enamine. Okay, enamine chemistry, imine chemistry. Give me a thumbs up if you follow me thus far on nitrogen nucleophiles, imine formation, enamine formation. Hopefully by now you spent some time looking at the mechanism of acetal formation that we spent a lot of time on Friday. And if you spent a lot of time on that, you'll notice that, once you get that down pat, the mechanism for imine and enamine formation isn't that much of a stretch. Okay, and if you really liked the mechanism of acetal formation, and we did spend quite a bit of time looking at that on Friday, we're going to turn around and go right back to it again. Because now we're going to spend some time talking about the hydrolysis of an acetal, right? We spent all kinds of time talking about how to make an acetal. We took a ketone or an aldehyde plus an alcohol, and we needed 2 equivalents of the alcohol, catalytic amount of acid. We formed a hemiacetal, then it kept going, then we formed an acetal, and we lost water in the process. Well, look at this. I can drive the reaction in the reverse direction if I do the reaction in water. And it's kind of fitting that David asked a really good question towards the end of the lecture on Friday. He said, Mr. Dion, what's about this removal of water? Where's the water going? And then we talked about how you do that using what's called a Dean-Stark trap. Now, if you think about it, if you don't have a way to remove water, you're not going to push the reaction in the direction of the formation of the acetal. So in order to remove the acetal or do the reverse of the acetal formation, you simply treat the acetal with aqueous acid. That's it. And then you're going to end up forming your ketone or aldehyde in 2 equivalents of the alcohol. And that's what's shown right here. We take our acetal plus water, a little bit of acid, stir it around, and we end up getting our ketone right back where we were. Okay. Now, it's also important that you understand that acetals only react under acidic conditions. In fact, some acetals are really labile to acid. I mean, exceedingly labile to acid. But I digress. You have to know that they're not going to react under basic conditions. Now, let's just move ahead here and take a look at the hydrolysis of an acetal and its mechanism. And if you've looked at this mechanism already, which I hope you have, because you should always be keeping up with the reading of the textbook, you'll notice that this entire mechanism is nothing more than kind of just the reverse of acetal formation. In fact, in the textbook, which I don't have open right now, but in the David Klein book, I do have it open, but it's something completely different. Anyhow, if you look at the textbook, he even goes on about this mechanism, and it's I can't tell you the page it's on, but it's right after the mechanism. I'll even read you what it says. It says, notice that acetal hydrolysis proceeds via a hemiacetal intermediate, just as we saw with acetal formation. In fact, all of the intermediates involved in acetal hydrolysis are identical to the intermediates involved in acetal formation, but in reversed order. This is illustrated in the following scheme. Now, he doesn't have a number for the scheme, but he shows you how it's literally the exact same thing, only backwards. And so if you feel like, oh, I spent a lot of time practicing this mechanism that you told me was important last Friday, well, it wasn't in vain, because the hydrolysis of an acetal follows the exact same rationale. Just the reverse process is all. We start out with a proton transfer. Then we end up losing our first alcohol here in this step. Okay. Then we have a nucleophilic attack by water, okay, followed by another proton transfer. That gets us to the hemiacetal, and then we have the 3 more steps, right? We have another proton transfer. We lose the second equivalent of an alcohol, and then we do a proton transfer at the end. Think about it. What was the first step in the formation of an acetal? It was protonation of the carbonyl. What's the last step here? Deprotonation of the carbonyl, right? Okay, anyhow, with that in mind, I told you we were going to get back to amine and enamine chemistry. Now, this is not meant to be anything complex. I just want to tell you that you can do the exact same thing with an amine or an enamine. Okay, think about it. When we did the amine or the enamine formation, remember that they always said, you know, minus H2O? Okay, I didn't really address it a whole lot, but you're going to have to remove water, much in the same way that we discussed with acetals. Thus, if you treat an amine or an enamine with an acid catalyst, but in water, okay, so we have water in there and we're not removing it, we're going to end up forming our ketone or an aldehyde, whichever we're starting with, okay, and we're going to get back our primary amine or our secondary amine, okay, and this mechanism is simply the reverse of the mechanisms of their formation. So that's why he doesn't even write them out in the book. He doesn't include the mechanisms for either of these. I think he might ask them in a question or something. It may be in the solutions manual, but he doesn't explicitly put it in the textbook. Now, I want to take a look at the next problem because I've taught this class long enough to know that sometimes students find this question challenging. And I'm going to show you probably some of the simpler ways that I know of to solve this problem, to solve these problems. Okay, who can tell me what functional group is in A? Not a trick question. It's a functional group we've looked at a bunch. Could anybody tell me what functional group is in A? Okay, if you're unsure about what functional group is in A, remember that when we have a carbon, okay, it has like 2 ethers attached to it. Come on, Apple Pencil. Okay, like that. And then we have 2 R groups like this. It's called an acetal. Okay, if we look at this carbon here, we have OR here, and then we have a carbon here and a carbon here. And thus, this is an acetal. Now, remember that when we treated an acetal, okay, with H3O plus, and if you're wondering, what about H3O plus? Well, look, all these reactions that we've been looking at here, okay, if you combine water and an acid, what do you get? H3O plus. If you combine water and an acid, what do you get? You get H3O plus, H3O plus. Thus, this is nothing more than a hydrolysis of an acetal. What happened when we hydrolyzed an acetal? If you hydrolyze an acetal, you end up forming, in this case, you'd end up forming a ketone plus 2 equivalents of the alcohol. And thus, we're going to do the exact same thing in this reaction. Okay, let me erase some of the spinach that I've got on here. Here's the carbon, okay? It's got the 2 OR groups on it. And thus, what our product is going to look like is we're going to have a 5-membered ring. That carbon will now have a carbonyl attached to it, so we'll get cyclopentanone. And then we're going to have the 2 equivalents of the alcohol. What is our alcohol? It's going to look like this. Okay? Like that, which is 1,3-propane diol. Okay? Now, if you want to write it out like this, maybe a preferred conformation, 1, 2, 3, like that. That works as well. Give me a thumbs up if that helps. That helps a little bit. Does that help anybody? Or if there's any questions, feel free to butt in at any time. And it's not butting in. You're paying to be here and spend a Monday morning studying organic chemistry. You deserve to ask as many questions. Good. Thanks, Emmy. That's great. Okay. So just to recap, okay, and this is for everybody. Just to recap, this is an acetal, right? And this is just hydrolysis. So hydrolysis of an acetal. We end up forming the ketone and the aldehyde. The next reaction, we're starting with what? Who can tell me what functional group this is? Not a trick question. Guy hates trick questions. Can anybody tell me what functional group that is? This is an imine, right? If we have an imine, it looks like this. Okay, like this. With this R group here, this R, it could be a carbon or a hydrogen. All right, so we have 2 R groups down here, and then we have something here. So this is an imine, sorry. Let me delete that. Now what happens when we hydrolyze an imine? Here's the carbon that's doubly bound to the nitrogen. And so we're just going to rewrite the carbon skeleton, 1, 2, 3, 4, 5, the double bond, and now it's going to be to an oxygen. Okay, now remember, an imine is formed from a ketone or aldehyde and a primary amine. And so we're also going to end up with the resulting primary amine, which should be this. And you're like, that looks like methylamine to me. You'd be absolutely correct. Does that one help? An imine being hydrolyzed in B? Hope so. Okay, let's take a look at C. I'm using the green pen for C. Could anybody identify the functional group in here? Does that look like a familiar functional group to anyone? I'll give you a clue. We spent a lot of time talking about this functional group on Friday. Yeah, thanks, Sean. Right? It doesn't look like some of the acetals we looked at, right? Because normally we had 2 R groups here, right? And then we had OR and OR. But now our R groups that I have highlighted in green, they're just 2 hydrogens. It's just 2 hydrogens. So when we hydrolyze that, we're going to have this carbon, okay, that I'm identifying by a little dot. We're going to have that carbon. It's going to have the 2 hydrogens attached to it, and it's going to be doubly bound to an oxygen. So this is formaldehyde. And then what's the alcohol that we're going to get? Well, if we draw that out, it's going to look something like this, okay, where we have our 2 methyl groups here and our 2 methyl groups like that. Okay, and so what's tricky here is identifying, it's kind of identifying the functional group. And the last one, we're starting with, in D, we're starting with an enamine. Okay, enamine, and so we break the bond from the carbon to the nitrogen, and that's where our double bond to oxygen will be. So we'll draw the ketone, and then we'll draw the secondary amine. God help me as I try to draw this to the best of my ability. Here we go, good enough for now. Okay, so we end up forming this compound, plus we end up forming NCH3 2H. So we form a ketone and a secondary amine. Give me a thumbs up if you're like, lock me in a room for a couple hours and I think I can nail this. I just need some more practice looking at and identifying the functional groups. Anybody? Okay. One person. Okay, I got a couple people. Good. All right, great. Wunderbar. Well, let's keep going and talk about sulfur nucleophiles. Good news here. No new, there won't be any new mechanisms in the sulfur nucleophiles. In fact, it's only a couple of slides. You guys remember acetal formation, right? We spend a lot of time talking about it. I can even add it up here on the slide if it helps. All right, we said, okay, if we take a ketone or an aldehyde and we treat it with 2 equivalents of an alcohol, if you're thinking, Mr. Dion, you're repeating yourself a lot here, that's no problem. No problem at all. Doesn't bother me one bit. So if we form an acetal from 2 equivalents of an alcohol and a ketone or aldehyde, okay, then I should put plus H2O over here. We can do the same thing with a thiol. This is called a thiol. It's the sulfur analog of an alcohol. And so we end up forming a thioacetal, which is the sulfur analog of an acetal. First question I was ever asked in a job interview after graduate school was about a thioacetal that I had made in graduate school, the project I was working at. Anyhow, what the heck was I talking about? Oh, I know what I wanted to say. The mechanism here, the mechanism is the same as acetal formation. Okay, so that's why he doesn't include it. It's the exact same, except you end up forming a thioacetal, which definitely has some different physical and chemical properties. And so you could either form your thioacetal like this, or you could use some kind of dithiol. So this is a dithiol. And then you can form a cyclic thioacetal. And we saw the formation of cyclic acetals as well. Okay, we spent time talking about that last class. Okay. I just want to point out one quick thing here that I don't even know if I've ever mentioned to a class before, but it's just something that just kind of piqued my interest. Is that if you notice, sometimes in the book he'll mix things up. Okay. Sometimes he'll write minus H2O like this in the mechanism or under a reaction arrow, and then other times he'll write it as a balanced equation. I just don't want you to be confused. If you're wondering, like, isn't there removal of water? Well, depends. If he writes minus H2O, then he doesn't write it over here. And if he doesn't write minus H2O, then he writes it as the balanced equation. Okay. Anyhow, I just don't want you to be like, oh, there's no water loss. Okay. Here's the new reaction that you're going to have to learn with the thioacetal, is that a thioacetal can be converted to an alkene with rainy nickel. So we take the thioacetal, and all you literally need to know how to write down is rainy nickel. Now, rainy nickel is interesting. It's like I've only used it maybe, if I was telling the truth, I would probably say twice in my entire life, and I remember trying to use it on a program in my 20s, and I'm in my 40s now, and it didn't work, so I just threw it away, forgot about it. But rainy nickel is pyrophoric, which means it ignites spontaneously in the air, and so not for the novice chemist to work with, that's for sure. And the mechanism is not covered in our textbook because it's definitely beyond the scope of anything that we would learn in organic chemistry too. The only funny thing I can tell you about rainy nickel is I worked with a guy in I worked with a guy in industry actually, who was PhD, really bright guy, and he told me he was singing the song by CCR. Does anybody know the song Down on the Corner Out in the Street? Is anybody aware of this? This isn't for points. Okay, so Sean says LOL, yeah. So he'd sing Down on the Corner Out in the Street, Willie and the Poor Boys were playing, rainy nickel can't be beat. Okay, I think the real lyric said something like bring a nickel, tap your feet, but he said rainy nickel can't be beat. Anyhow, all right, funny guy. Okay, anyhow, but you know what, that guy, I think he probably was an expert in using rainy nickel because I think he had used it a lot in grad. And if you're really paying attention, you'll see, okay, this gives us another method for reducing a ketone or an aldehyde to an alkane, right? You treat it with a catalytic amount of acid, your dithiol, you make your cyclic thioacetal, hit it with rainy nickel, and you're done. Okay. And if you're one of those people, and there's very few students that are like this, to get frustrated when they have to learn more than one way of doing something, because now you've got rainy nickel, right? You've got Clemenson reduction, reduction. And you've got the Wolff-Kishner, okay, Wolff-Kishner, which are all ways of doing the same damn thing, right? Taking a carbonyl and reducing it. But remember, a good organic chemist always needs to have a few ways of doing everything. So these are all reductions of carbonyls, 3 of them already that you've learned just in, maybe in the past 2 weeks. Because what did we learn Friedel Crafts, a couple weeks ago or a week ago or something. Anyhow, this is if you didn't like the last question, I know you'll like this one because I've taught the class long enough to know that most students enjoy this question. Not much to it. All you have to do, look, when you're taking a ketone, right here we have a ketone, here we have an aldehyde, you're making a thioacetal, and then you're hitting it with rainy nickel. Do you want me to show you the fastest way to answer this problem? Who wants to see the fast way? Anyone? Okay, David says me. Look, David, here you go. Okay, redraw the ketone. Okay, you with me, David? We're going to redraw the ketone. Can you guys see when I select the eraser? So this is the pixel eraser. Watch this, David. Here's the answer to the question. Scrub, 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 scrub. There you go. There's the answer. Okay, watch. We'll do it here too. We'll redraw the starting material. Put the carbonyl here. I'll grab my eraser. Scrub, 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 scrub. There you go. Those are the 2 answers. Done. Give me a heck yeah if you like that. Rainy nickel. Okay. Carbonyl reduction. Anyone? All right, cool. All right, Cha, heck yeah. I like it. I like Cosmo Kramer. He's hilarious. Okay, I think everybody likes Cosmo Kramer. Okay, let's see. Yeah, it's just, it's chemistry that students like because it's not super complicated. The only thing that's kind of missing in my structure in the end is not really technically correct. There should be another hydrogen here. Okay, so if you want to draw it correctly, it would just be this 2-methylbutane, okay, like that. Anyhow, but that's all you have to do is grab the old eraser and scrub off the carbonyl and you're done. Okay, we're in section 19.9 now, which deals with hydrogen nucleophiles. I'm going to go over this part maybe a little bit quicker because we've already looked at these before. And it even says here, recall that aldehydes and ketones can be reduced to alcohols using a hydride. And the 2 hydrides that we looked at way back in chapter 12, which was the alcohols chapter, were lithium aluminum hydride and sodium borohydride. Lithium aluminum hydride is a lot more dangerous. It's a 2-step process. First step is to treat it with the LAH. Second step is to treat it with water. So that's 1 step at a time, okay? And the only time you throw water in is you want to be very careful while you're doing that. So lithium aluminum hydride, we abbreviate that LAH. Sodium borohydride, that can be done in a protic solvent like methanol or water even. But it says here, these reductions are carried out under basic conditions because hydrides are strong nucleophiles. What's kind of interesting is that in the textbook, he even goes into he talks more about the mechanism in this chapter than he did in the alcohols chapter. And he said, well, this is a heavily studied mechanism. And what I mean is the mechanism that you're looking at on this page is a heavily studied mechanism. There's a role of the cation, lithium, as a Lewis acid. Then what are called crown ethers can play a role in these reductions as well. But he said this is a simplified version of the mechanism, what you're seeing right here, because if you're looking at it thinking, that's only 2 steps, I can do that. Absolutely. And this mechanism will suffice. It's also what he says. So I like the way David Klein puts things sometimes. Anyhow, so we take our lithium aluminum hydride. Hydride gets delivered as a nucleophile. We make this negatively charged species here, right, because we're in base. And then we do a proton transfer. And there you go. There's your alcohols. And again, this is a mechanism that we looked at in detail. I'm going to move on to the next slide, which just discusses the fact that the carbon of a carbonyl has sp2 hybridization and is thus trigonal planar. And so that hydride, right, that nucleophile, can attack from either face of the molecule. So in this case, since we're making a stereocenter, the hydride could be delivered to either face of the molecule with equal probability. And again, we'll end up with a racemic mixture of stereoisomers. Let's see here. This is another one here that is, again, more review. I noticed there's a big mistake on this slide because it's not very polite to write a person's family name with a lowercase letter. So I'll put a big capital G here for Victor Grignard. Okay, there we go. So Victor Grignard reagents attack ketones or aldehydes to make an alcohol, form a new carbon-carbon bond. We spent a lot of time talking about Grignard chemistry earlier on in this class, so nothing really new there. Here's this again, the mechanism of the Grignard reaction. Again, this is probably a simplified version of the mechanism, but it will suffice. You have nucleophilic attack by the Grignard, which we treat as if it was a carbanion, and then we have a proton transfer in the second step. I just want to back up and remind you that Grignard chemistry is a two-step process. Okay, first step is addition of the nucleophile, then you add water. Again, same thing here. First step is addition of the Grignard, and then second step is water. And that's what's being shown here in this mechanism. The first step is the nucleophilic attack. The second step is you would add water to do the proton transfer. Okay, so those are all things that we've looked at. Let's talk about something that's new, which is cyanohydrin formation. If there's one thing that's replete in the, or there's one thing about chapter 19 is that it's replete with new functional groups. Here's a brand new one for you, which is the cyanohydrin. Cyanohydrin shown here. And there's quite a bit of detail about this in the book. It says the cyanide ion. So you should know what a cyanide ion is by now. That's a polyatomic ion that you would have learned way back in Gen Chem 1. And you should be able to draw the Lewis structure of the cyanide ion like this, okay? Put it in brackets. Is also a carbon-based nucleophile and reversibly adds to ketones or aldehydes to form a cyanohydrin. Now this is with HCN. HCN has a boiling point of around 26 degrees Celsius, so not a lot of fun to work with. It's so volatile. The reaction works better under basic conditions, and so when this was originally developed, it was run with a small amount of base to deprotonate the HCN and to produce the cyanide ion. Here's the nucleophilic attack by the cyanide, and it says that you don't have to use an acidic workup because HCN serves as a source of protons. We just have enough HCN in the reaction mixture that we can do another proton transfer and end up with the, what's this guy called here? The cyanohydrin. Okay, so cyanohydrin formation. Now, I have some notes written down here about cyanohydrins because there's quite a few different ways that he shows to do this chemistry in the book, and I'll go over them with you quickly here. But it says that in order to achieve basic conditions, potassium cyanide is usually used along with HCN. So instead of just using HCN and a base, we use cyanide ions and then HCN. And this way you have more of the cyanide than you do of the acid. And so to do that, you would just use potassium cyanide and HCN, hydrogen cyanide, and you end up forming a cyanohydrin. In both of these reactions, there's nothing wrong with either of those reactions at all. But what I would point out is that I think there's an even better way, and it is mentioned in the book. So I'll show you what it is. If you wanted to do this same reaction right here, okay, you take acetone and you treat it with KCN, potassium cyanide and HCl, okay? And if you use potassium cyanide and HCl, the advantage of doing this, reaction in my mind is that you avoid using what? HCN. Again, HCN is a mess to work with, okay? The boiling point is so low that it's going to vaporize and it's poisonous, obviously. And so, you want to be really careful around HCN. In fact, you've probably heard of the gas chamber, which was used in California to execute criminals, a long time ago. I don't think it's used anymore, but that's what they used, was HCN gas. And they just made it by reacting potassium cyanide with sulfuric acid. Anyhow, That's not a happy thought for a Monday, is it? You might be wondering, what could I do with a cyanohydrin? Well, there's a couple of reactions that you need to know. One is that you can reduce the cyano group using lithium aluminum hydride and water to make a primary amine. And you could also hydrolyze the nitrile using acid and heating that up, and you make a carboxylic acid. Now, you might be wondering about the mechanisms of these reactions, but these two reactions will be discussed in even more detail in the carboxylic acids chapter, which is chapter 20, the next chapter. Okay, now let's switch gears to section 19.10, which discusses the Wittig reaction. This will probably cover, most of the rest of today's lecture. Because section 19.10 is kind of a long section, and it's an important section. Wittig chemistry always comes up on the ACS final. And if you are currently enrolled in chemistry 3112, this is the last wet lab that you'll do before the laboratory practical. It's the Wittig reaction. Very important reaction. And it says here, the Wittig reaction is an extremely important reaction in organic chemistry like Grignard, in that the carbon skeleton is modified. You take a ketone or an aldehyde and you convert it to an alkene with the formation of what? Ooh, a new carbon-carbon double bond. Didn't I tell you guys that if you could find a way to make carbon-carbon bonds, you'd win a Nobel Prize? Well, Wittig won the Nobel Prize, so he got Nobel Prize in 1979. He shared it with Herbert Brown. But anyhow, you got a Nobel Prize for it. Yeah. And, if I was where you are in school, I'd probably be looking at this thing right away and be like, what is that? What is this interesting looking molecule here, this Wittig ion? Well, we're going to discuss what that is. And this is called an ylide. Let's look at the ylide. The Wittig reagent is a phosphorus ylide, that's how it's pronounced, in which a carbon atom acts as a nucleophile. Think about it. If we have a negative charge on a carbon, well, yeah, it's going to act as a nucleophile, right? Okay. And you probably also looked at that, maybe on the last slide and said, why do you draw it as this Wittig ion when you could just draw this resonance structure here, and then you have something without a charge? Wouldn't that be preferred? Well, remember, carbon is in period 2, and phosphorus is in period 3, and so the orbital overlap will not be very good, and so in fact this will probably be the major species. Okay, would be the ylide, and this part over here, or this resonance contributor, we call this the ylene and the ylide. All right, now what about the mechanism? The mechanism is likely a 2+2 cycloaddition between the Wittig reagent and the carbonyl group of our aldehyde or ketone. Think about it. You've got something that's strongly nucleophilic, okay? This is going to be a very good nucleophile, right? It's got a negative charge on it. If you have a carbonyl, whether it's an aldehyde or a ketone, you know that this carbon is delta plus. So the first step is going to be, it's going to be a nucleophilic attack on that carbonyl, right? So let's take a look at the mechanism. I don't want to have too many arrows drawn off one compound. Here's the mechanism. You definitely have to know the mechanism of the Wittig reaction. Here's the 2+2 cycloaddition, right? 1, 2, right? We got 1, 2, and 1, 2. And we have the cycloaddition. We have the carbon with the negative charge attacking the carbonyl. And then we draw a curved arrow from the pi bond. And I like to draw this arrow. I don't draw it the way that he has it. I mean, what I like to do is this, is I take this double bond and then I drag it through the oxygen to show that the bond is formed between the oxygen and the phosphorus like this. We end up forming this interesting cyclic intermediate, which is called an oxyphosphatane, which undergoes fragmentation. Now you might be wondering, what's the driving force behind doing all of this? And that's the formation of this piece of crap over here. Now, you're like, Mr. Dion, why are you cursing at a molecule? This is called triphenylphosphine oxide. Triphenylphosphine oxide. Okay, which we abbreviate TPPO because it's so annoying to write out. The reason I don't like this molecule is because it is the bane of an organic chemist's existence. I've done a lot of Wittig chemistry in my time, and removing triphenylphosphine oxide from a reaction mixture is sometimes it can be easy, yes, and of course the experiment that you're going to do in 3112, we set it up so that the purification is, very, very, very doable, but it's pretty difficult to remove it sometimes, and I had a lot of hard times in the lab trying to remove triphenylphosphine oxide from products. Anyhow, what's the net result? Okay, what's happening here overall? If you look at it carefully, what you're doing is you're adding this part, this CH2 is getting replaced, is replacing that oxygen, is what you're doing. So that's it. Okay, the formation of the especially stable triphenylphosphine oxide, right, which is our TO. Byproduct derives the equilibrium to favor the formation of the desired alkene. Now, there we go. How would you go about making a Wittig reagent, the illid, okay? So we call that a Wittig reagent, and it's actually a two-step synthesis. It's not that difficult to do, I guess depending on what Wittig reagent you want to make. But you take triphenylphosphine, so PPH3. So this is triphenylphosphine, and you treat that with your alkyl halide. It's an SN2 reaction, so SN2 rules are going to apply, in that you either have to have a methyl halide or a primary alkyl halide. You do the SN2 reaction, you make a phosphonium salt, right? You have a positive charge here and a negative charge here. You make a phosphonium salt. Then you do a proton transfer using this. So this is called butyl lithium. This is actually called N-butyl lithium. Okay, so this is N-butyl lithium shown right here. You deprotonate and you make your Wittig reagent, and there you go. Again, the first step is an SN2 substitution. So primary halides are more easily made into Wittig reagents than secondary halides. In fact, I've looked at the ACS final enough times by now to know that this is one of the things they love to ask is, what's the most efficient synthesis of a Wittig reaction, or a Wittig reagent rather, and all you have to know is that the first step is an SN2. So you would pick the least hindered alkyl halide. Now, what about the stereoselectivity of this? Wittig reaction is a particularly useful reaction because it installs a carbon-carbon bond at a very specific place where the carbonyl was, and the Wittig reaction is stereoselective. Using a Wittig reagent derived from a simple alkyl halide, the Z alkene is going to be preferred, right? Z is for zusammen, or together. Okay, so if you have something really simple, like just a methyl group, then you're going to have that, methyl group on the same side, okay? And we end up, so these two groups are Z, right? Zusammen, okay? Now, there are many cases where you end up with the E product. If the Wittig contains an electron withdrawing group, the E alkene is going to be the major product. An ester is an electron withdrawing group. And so when we react with this Wittig reagent, we end up with the E product. Look, you can see the two bigger groups are opposite, right? They're on the opposite sides. Also a phenyl, that's an electron withdrawing group. And so these two phenols will end up on opposite sides like this. These are rules that you have to know. If you have an electron withdrawing group, you're going to get the E product. The electron withdrawing group, or a phenyl ring, delocalizes the anionic charge on the Wittig reagent, and that's going to stabilize it. Now, the whole mechanics as to why you end up with the E product or the Z product is not covered in this class. It's beyond the scope of our class. But if you have a really inquiring mind, you could just do a quick Google search and you can find the rationale as to why that is. Again, it's not covered in our textbook, and so you don't need to know it. There's a variant of the Wittig reagent called the Horner-Wadsworth-Amine reagent, which is similar to a stabilized Wittig reagent. and it also yields E-alkene. So anytime we have any kind of stabilized illid or stabilized Vinegary agent, we end up forming the E product. In fact, most of the time with Greenyard in this class, you can usually just guess that it's going to be the E, and you'd be right, probably in more than 75% of cases. So here we have our electron withdrawing group, okay, right here, our ester. And so that's our stabilized Wittig. And the Horner-Wadsworth Amine is called a phosphonate ester. So we have a phosphonate over here, and then we have an ester over here. And so it's yeah, the Horner-Wadsworth Amine's reagent will also give you the E. So both of these will give you the E products. Here's an example of a Horner-Wadsworth Amine's reaction. So again, it's just a variation on the Wittig reaction. The Horner-Wadsworth Amine's reagent gives the E-alkene as the major, like a stabilized Wittig reagent does. And so when we're adding the ester, so if you're wondering, like, what's happening in this Wittig reaction, right? Think about it. From the carbon that's got the negative charge to everything on the side that doesn't have the sulfur, right? That's going to take the place of this. Okay, so what's in that big green circle is going to take place of the oxygen that's in the little green circle. That's it. Choice of solvent and Lewis acids can also affect the stereoselectivity of the Wittig and Horner-Wadsworth Amine's reactions. The take-home message here is you need to know what's in our textbook, nothing beyond that scope. But as you can see, there's a lot of information and there's a lot of research that's been done with respect to Wittig and Horner-Wadsworth Amine's reactions and their stereoselectivity. Again, this is the part that I will probably ask you about on the next quiz, or this is one of the things I'll ask you on the next quiz, and this always gets asked on ACS finals. Retrosynthetic analysis of this alkene in the green box reveals that there's two possible routes to make this alkene doing a Wittig reaction. I could either use route number 1, which would use 2-butanone and this Wittig reagent, or I could do route number 2, which uses formaldehyde and this Wittig reagent. Here's what you've got to be able to do. To determine which one of these routes is better, number 1 or 2, you look at the alkyl halide that you would have to use to make the Wittig reagent. So that's why I highlighted the Wittig reagents. You've got to look at this Wittig reagent. You've got to look at this Wittig reagent right here and this Wittig reagent right here. And you've got to say, which one of these would be easier to make? Could anybody guess? Anybody figure that? Would it be the one in yellow or the one in green? Remember, the first step is an SN2. Does anybody have an inkling about that? Eric, you're right, and your rationale is also correct. Amy, same with you. You're both correct. The answer is the first one would be much easier, right? The first one can be made from an SN2 using a methyl halide. The second one, we'd have to use a secondary alkyl halide. Let's take a look. In route number 1, we could use a methyl halide. Again, it could be methyl iodide, methyl bromide, methyl chloride. I don't care. Okay. And the first step is to treat that with triphenylphosphine. Let me draw. I don't know why they don't draw these with bonds sometimes. Irritating. Anyhow, the first step is this. Look, you have a lone pair on the phosphorus. It's going to do a nucleophilic attack. That's going to be a beautiful SN2 reaction. Okay, because that's a methyl halide. If we have a secondary alkyl halide, we're going to do an SN2 reaction, but it's not going to function nearly as well, okay? Because it's much more hindered, as Eric said. And so, right? We'll put here more hindered, like that. Okay? There we have it. Here's the overall synthesis of the alkene using the Wittig reaction. Let's start with iodomethane, treat it with triphenylphosphine. Let's draw the mechanism again. We take our our methyl iodide, and we have our triphenylphosphine. Put in there a lone pair. Here's the first step. Follow me, people. Nucleophilic attack, loss of leaving group. Let's draw what you'd end up with. Let's look very carefully. You'd have CH3, okay, like this. I'm going to draw all the protons in explicitly on purpose. Just wait and see why. Then you've got a phosphorus that's got 1, 2, 3, 4 bonds. Phosphorus is in group 5A. When phosphorus has 4 bonds and no lone pairs, it's got a positive charge. That means that this whole molecule has a positive charge. How do we equal that, or how do we balance out that positive charge? We're going to take butyllithium, okay? I'm going to write it out like this. 1, 2, 3, 4, like this. I'll put the negative charge. I'll leave the lithium out. And we're going to end up ripping this proton off like that. And then we're going to have this CH2 with a negative charge on it. Our phosphorus. I'm going to condense all those. Okay? And that's our ylid. Capiche? Caposh? Okay, let's draw the arrows for the next step. I'll use blue arrows here. Now you're going to form the oxyphosphate nucleophilic attack. Okay, you've got these lone pairs on the oxygen. The pi bond's going to break. It's going to come down here. Then you're going to form the oxyphosphate. Okay, let's draw that. Be careful here. Let me see. We'll draw it like this. There. There we go. Okay, like that. So there's our oxyphosphate. And now we just get a rearrangement. We're going to form triphenylphosphine oxide, and we're going to form our double bond. Keep in mind that this carbon right here, that's this carbon here. Okay, and then after that rearrangement, you're going to form this alkene, plus you're going to form double bond on the phosphorus and pH. No, you're getting ahead of yourself. There we go. Like that. Okay, that's the whole mechanism from soup to nuts.